Thank you very much to see that you survived and you came for the whole lectures. It's really something. This is the set of the 4 lectures that I gave. So today I'm discussing this topic, this Efimov Physics from other perspectives. And before going on, as usual, it's really a pleasure to thank again and again people that I had a chance to discuss and collaborate with. So for this specific part, the heroes, my heroes at least, are especially Omri Ovdat and Dor Gittelman. Since there were people that came and perhaps missed some of the lectures and some of the salient points, so I will give you a brief digest of some previous results. So for those of you who were, it may be boring, but again, you know. So again, as opposed to Euclidean spaces, which are characterized by translational symmetry, as we said again and again, fractals possess dilatation symmetry, meaning that they are self-similar objects. And again, this idea of self-similarity is very well accounted for by this picture of the Sierpinski gasket, which is self-similar, which means that if you enlarge again and again a part of it, you in fact get back the same whole picture. So this is a discrete scaling symmetry as opposed to continuous scaling symmetry or invariance. So again, let me restate the main idea. The main idea of discrete scale invariance is an invariance that is expressed by a weaker version of scale invariance, which means that there are quantities that obey this simple scaling equation, but where now A and B are fixed, instead of being instead of being satisfied for any real B function of A, for continuous scale invariance. That's the difference. Okay? So I gave a few examples of this discrete versus continuous scale invariance. So the case of the Cantor set, the triadic Cantor set, is a case of a discrete scale invariance, which means that for the mass of this object, we have indeed this kind of scaling relation, but here A and B are fixed to those values 3 and 2. They are not whatever I want. On the other hand, if I'm looking at the one-dimensional line, then I could also write something like this, which is again a scaling function, but this is, I can choose whatever B of A that I wish. The same for two-dimensional examples, this Sierpinski gasket and this graph, so to see the difference between the two. Okay, so now we solved this equation in both cases, and we saw that for the continuous case, a general solution is just a power law with an exponent that depends on B and A, whereas for the discrete case, with fixed A and B, the general solution is again this power law with the same exponent, but now it's multiplied by this function, which is periodic function of period unity and function of the logarithm of the variable x. So power laws are signature of scale invariance, either continuous or discrete, but this function is specific for the discrete case. Okay, so now what I would like to address is the following question. Is it possible to break this continuous scale invariance into a discrete scale invariance? That's the idea today. Okay, another thing that I discussed in the first lecture is that due to this periodic function that we have here, that is in this solution, we can just Fourier expand it, and the same solution here can be just described by saying that a scaling function is characterized now by an infinite set of complex valued exponents. So this existence of such an infinite set is sometimes taken as a definition of an underlying fractal structure. And what we can say is that power laws with complex valued exponents are a signature of discrete scale invariance. So what I want to convey is just to imprint on you this instinct that each time that you see a complex valued exponent, you say, there is a fractal there, because Akkermans for 4 hours just told us that each time that there is a complex valued exponent, there is a fractal. So this is the idea, okay? So, and we will see some of them. Some are expected, but sometimes some are unexpected. Okay. So today's program is to investigate, as I said, situations where continuous scale invariance is spontaneously broken into discrete scale invariance, and to discuss physical examples where this occurs. And I will call them generically Efimov Physics. You will see why. And then I will just rephrase those physical examples using renormalization group, language, and the language of limit cycles. Okay, so now it's part 2. Again, for those of you that were in the first part and just fell asleep a bit, now you can wake up. And this is new stuff. Okay, so a simple example of continuous scale invariance, sometimes also it's known in the literature as conformal invariance in quantum physics. So I want to illustrate those ideas on a very simple example in quantum mechanics and on a problem that looks apparently simple, which is a problem of a Schrödinger equation for a particle of mass mu in d dimensions and with an attractive enough, we'll see why, potential that falls like 1 over r squared. So it's not a Coulomb potential. So the Hamiltonian of this problem is this. It's a very simple problem. Okay? And by redefining the energies, we can just rewrite the Schrödinger equation that is associated with this Hamiltonian under that form, where L here is the orbital angular momentum, and I took h bar is equal to 1. Okay. Now, so this is the same Schrödinger equation written in a more compact way, where I just put together in this parameter, zeta, both the potential energy and the centrifugal barrier. And this equation, this Schrödinger equation, displays an unexpected behavior that is distinct from Hermitian Hamiltonian eigenvalue problems that we're used to, mainly due to one first reason, which is that the parameter that is here is dimensionless, which means that this problem does not have any characteristic energy or length scale, and like, for instance, in the Coulomb potential, and this is because the 1 over R2 potential has the same dimension as this, which is also 1 over R2, or this one, which means that this parameter is just dimensionless. Okay? So there is no characteristic length in this problem. And as a consequence, this Schrödinger equation displays continuous scale invariance, meaning that if now you change distances into lambda times distances, whatever is lambda, or wave vectors in 1 over lambda wave vectors, then what you see is that to every normalizable wave function, which is solution of this Schrödinger equation, corresponds a family of wave functions of an energy that is shifted also multiplied by this lambda, which is solution of this Schrödinger equation. And the consequence of this is that if you can show that it exists one bound state in this problem, then it implies that it exists a continuum of related bound states, which means that there is no ground state in this problem. So it's a problem, in principle. Okay, so this problem, this weird behavior, is in fact related to the fact that this Hamiltonian is not self-adjoint over the space of square integrable functions. Okay? And this is a property that a lot of potentials, such potentials have. For instance, if you look at potentials which decay even more rapidly, they have also this problem of self-adjointness. And we know how to solve this kind of problem, so now it's I mean, there are things that are obvious from basics in quantum mechanics, but that we forgot with the years, okay? So we know how to solve this kind of problem, and we know that if we add further restrictions on the space on which this Hamiltonian operates, it's always possible to define a family of new operators that are parameterized by something that I call theta, which are associated to this Hamiltonian and are self-adjoint. Those restrictions show up, in fact, as new set of boundary conditions that are specific to each of those Hamiltonians H theta. And all operators H theta, in fact, have the same formal expression as the initial one, but they act in another space, another L2 space, which is the space restricted by the corresponding boundary conditions that we use here. And those operators are called self-adjoint extensions of H. So far, so good. This is basic quantum mechanics, the way that we love it. Yeah, okay, good. Now, let me summarize all what I said. I said that if I look at this Hamiltonian with this 1 over r squared behavior, this Hamiltonian is scale invariant and not self-adjoint. And this leads to the remarkable result that if this zeta, which was defined here, you remember, is larger than a given critical value, which is equal to that, then boundary conditions needed to find self-adjoint extensions, in fact, break continuous scaling invariance that we have into discrete scaling invariance, which means that each time that you want to choose self-adjoint extensions such that the problem is defined, then you will break this continuous scale invariance. I will show it why. So this is just a conclusion, a summary. I summarize what I said. Now, as a result, the energy spectrum appears in the form of a geometric sequence. So this is the spectrum that we will get. I will derive it. Just, I didn't say it for the moment. It's just the result. And this discrete spectrum, in fact, is a result of this discrete scale invariance. Now, this is a very generic feature. It is called, so this, first of all, this spectrum does not have a ground state. So this we noticed already. And the breaking of continuous scale invariance in the quantum domain is sometimes called the scale anomaly. Okay, so this is something that was very much popularized in the 70s by Roman Jakiv, for instance. Okay, so an example of such quantum anomaly is provided by the so-called Efimov effect. So again, I know that here there are a lot of experts of the Efimov effect. I'm not an expert, so I will be brief. And I'm brief because I'm not knowledgeable, okay? And so this Efimov effect occurs in the non-relativistic quantum three-body problem. And what Efimov noticed back in 1970 is when analyzing the three-nucleon system interacting through a zero-range interaction, this is the range of this interaction, and he pointed out the existence of a universal physics at low energies, whereas people were mostly interested in high energies, which is also singular. And he saw that if we look at energies which are much smaller than this characteristic energy, which depends on the range of the interaction, then when the scattering length A of the two-body interaction becomes much larger than the range of the interaction, then there is a sequence of three-body bound states whose binding energies are spaced geometrically, which means with the kind of spectrum that I showed before. And those energies are just in between those two energies, which are set by the scattering length A and the range of the potential R0. Okay. Now, so this is the result. When A, the scattering length, increases in absolute value, you get new bound states that appear at values, critical values of the scattering length that we call A star. And those critical values differ by a multiplicative factor, which is this factor, which is universal, where this number is equal to this. So just universal number. And those are the energies. So you see that this is the Efimov spectrum that I just described previously in my summary, in my brief summary. And you see that when you change the scattering length, then you have each time a new state that pops up, and eventually you have this geometric series here, which of course is not on scale with this factor, but you understand what is going on. Now, what Efimov showed is that the corresponding three-body problem reduces to a simple Schrödinger equation, so which means instead of solving a very complicated three-body problem, you can, if you are at short scales, you can in fact reduce it to a simple Schrödinger equation with an effective attractive potential which has this form, which is precisely the 1 over r squared that I discussed before. But now the strength of this potential, what I call psi, now is related to this parameter S0, which depends on the three-body problem, the initial three-body problem. So this is, I would say, on one leg. This is a Talmudic expression. But OK, it fits for Efimov. And these Efimov quantum states have been beautifully evidenced by several very nice experiences, one by Rudi Grimm and co-workers, one by Randy Hewlett, and in ultra-cold gases using Feshbach resonance. But again, I think that those topics have been extensively covered here and elsewhere, or will be. For instance, in the course of Jean, I mean, you will not discuss this perhaps, but I don't know. But things that are necessary to understand this physics. OK, so let's now go back to our spectral problem. So this was just for amusement, and now let's work again. OK? So I remind you that we have this Schrödinger equation with this parameter, which is dimensionless. And my pointer does not work anymore. But OK, so I don't know. No, I mean, OK, I can manage for the moment. Huh? So anyway, merci Jérôme. OK, good. So back to our Schrödinger problem, where this parameter zeta encapsulates both the potential energy, this 1 over r squared, and the centrifugal potential barrier. And now we want to solve this, this equation. So we look for bound states, which are normalizable. So the general solution is a linear combination of something that is not that ugly, but it's called modified Bessel functions. So those are those functions. And those functions depend on this parameter, which is written here. This zeta is just this zeta. Okay? And now we assume that zeta is larger than this value, which means that this lambda squared is positive. Okay? If we assume this, then this function diverges for r goes to infinity. Therefore, we need to take this parameter C2 to 0 in order to have normalizable wave functions. And what remains is only this part. And this part, close to 0, behaves like a nice power law, something like this. And therefore, if you want to use this in order to get quantization condition, you cannot. And this is just a way to say that Hamiltonian is not self-adjoint. You cannot get a good quantization condition out of this. OK, so what is self-adjoint? Something that we're used to play with. It means that an operator and its adjoint are equal, and their space of definition are also the same domains. Okay? So this condition can be rephrased using just those functions that I wrote just before as this guy being equal to 0, where again, you know, those parameters are defined here. And when you try to get this equal to 0, you get that this quantity is equal to just the sine of lambda log of this ratio of K1 and K2. And this usually is different from 0. There is no way, not 0. Okay? So what we call the integrated part that usually falls down, here it has no reason to vanish. And therefore, H is not self-adjoint because this is not 0. This is not equal to this. Okay? So to cure this, we add the additional boundary condition, and this additional boundary condition is very simple. Now we want to force this to be equal to 0. So if we force this to be equal to 0 for any K1, K2, K1 different from K2, then what we get is that this ratio should be equal to that. Okay? And this means that the energies are equal to some value times this exponential of pi n divided by lambda, where this lambda again is this universal parameter here. Okay? Very simple. Okay, so this is the meaning of self-adjoint. Now, in order to have self-adjoint extensions, the spectrum is given by this discrete spectrum. This K0 is in fact an arbitrary energy parameter introduced for dimensional consideration. This is called the Efimov parameter. And this Efimov parameter should be determined, cannot be determined here, and it should be determined by an exact solution of the three-body problem, which takes into account properly the short distance physics, which cannot be 1 over r squared all the way down to 0. Okay? So this could be a nice exam problem for quantum mechanics, right? Okay, so this is called the Efimov spectrum. So this spectrum is discrete. This is a geometrical series, okay? And this Efimov spectrum has the following characteristic. First of all, it is invariant under a discrete scaling, discrete rescaling with this fixed parameter. What is the meaning of this? It means that if I take those values here, then if I multiply by this specific parameter here, not any parameter, then I generate, in fact, Kn plus 1, which is the same. So this spectrum is discrete scale invariant. So I broke the continuous scale invariance into a discrete one. Now, the eigenfunctions also possess this property. So those are the eigenfunctions for any value of r. They are also invariant under the same discrete scaling transformation. And if you want to see this, that you don't like modified Bessel functions, you can look at it for small values of r, and you see that, in fact, this function is this cosine of lambda log of kr, which is indeed a log periodic function of this argument. This is just single harmonic approximation of it. So all this has all the features of an underlying fractal structure. Okay, but there is no fractal here. The density of states has the same property. If you define the density of state as usual as being a sum of delta functions, then if you scale the energies by, again, the same parameter, you see that the density of states obeys this scaling equation, and we know that the solution of this is indeed the power law times log periodic oscillations, which is just solution of this, where lambda is fixed. It's given. And in conclusion, the original continuous scaling symmetry, which was this symmetry for any lambda, is broken into discrete scaling symmetry, which is given by this discrete spectrum. So here we have, in fact, a possible underlying fractal structure. The question is, what is this structure? And the answer is that I don't know, but this is left to you as an exercise. It's a homework. Okay? What is the fractal that is underneath? Okay, so now for people again that got lost in the part 2, you have another chance in part 3, which is in fact rephrasing exactly the same problem, but from another point of view. Now this point of view is point of view for normalization group, RG, and limit cycles. So why to do this? Why to use this language of renormalization group? There are several reasons. One reason is that it provides another point of view on this problem of this attractive potential, which I guess is perhaps more physical. Second, it allows to insert that problem in a broader perspective. And third, it makes a connection with other physical problems. And you will see that there is a long list of such physical problems. And I guess some of them even you did not expect them. Okay, so let's go and see. So again, what I said before is that the need of self-adjoint extensions results from the fact that there is a hill-defined behavior of the potential when r goes to 0, and there are no characteristic lengths in this problem. So this is the basic disease of this problem. To cure those problems, now what I want to do is something else. I want to introduce a short distance cutoff that I call L0, so that now I define a potential which is a long-range potential at distances that are larger than this L0, which is our initial potential, and a known short-range structure at distances which are shorter than L0. Okay? So I just define a given L0 like this. Just note now that here I put r to the power s instead of 2 in order to give dimension to this parameter for a short while. But don't worry, eventually s will be equal to 2 again. Okay? So this is the idea. And this cutoff L0 is a physical parameter. It's a characteristic scale at which the potential VL, long range, is altered as a result of the additional short-range interaction. Okay? So it tells me that below L0, something happens which is not very universal, and I don't want to know what it is. Okay? Now, is this clear? Yes? The Schrödinger equation becomes just the Schrödinger equation that we had before, just that now I have this r to the s. But now it is defined for r between L0 and infinity. And I impose on it mixed boundary conditions. Mixed boundary conditions means that they are not zero boundary conditions, what is called Dirichlet boundary conditions, not Neumann boundary conditions, but something that is a mix of both. And this defines a parameter that is called G0 here, by definition. And all this encodes the short distance contribution that I don't know. Okay, you are with me? Okay, now, once you have this, you get a complete solution of the problem. And this complete solution is a function of the set of parameters that I just defined, which is this scale, cutoff scale L0, the parameter of the potential, the strength of the potential, which is xi, and this G0, which is here. Everything is well defined now. Okay? So now, next step, I want to make a renormalization group transformation, meaning that I want to change the cutoff distance from L0 to some L. Okay? And I want to integrate out all the distances that are between this L and L plus some DL, and obtain an equivalent effective description, but with a new cutoff that now I call lambda L, whatever lambda is. Okay? And a new set of boundary conditions. Now, for this new cutoff scale, there is a new parameter G that is now not G0, but it's G of lambda L. And like this, I can solve again the problem. I get the same problem, but with a new set of parameters, and I can solve it. So there is a new Schrödinger equation that now is defined in this range instead of L0. And there is a new coupling constant and a new boundary condition, G of L. I remind you that this xi is the strength of this potential that we had at the beginning, this xi. Okay? Good. Now, by doing this rescaling the size with this lambda, which is continuous, whatever you want, and the energies, in fact, we get an equivalent, unchanged Schrödinger equation, provided that we just rescale the strength of the potential like this. And now, this is why I took this S, because now xi has dimensions, and now I have to rescale this xi when I change the scales. You see that if S is equal to 2, then this remains invariant. And to rescale the strength of the potential is to say, in fact, that xi depends on the scale, on the cutoff. This is equivalent to this, is to say that it depends on this, and it depends that way. Okay? Now, you can do exactly the same with this boundary condition function, G of lambda L. You can relate it to G of L, and if you do the same as we did here, this is the equation that you obtain. Okay? And those two previous equations, this one and that one, are called the renormalization group equations of the problem. And we define the so-called beta functions. And those functions are defined just as logarithmic derivatives of those two quantities with respect to L. And if I just rewrite those two equations using beta functions, so you see that this function is just beta is equal to 2 minus s psi, and this just is this equation. Okay, so those are called renormalization group equations. Now, so those are renormalization group equations. So now I take back this s equal to 2 in order to describe the potential that we love. And by doing this, this just will be 0. And now I assume low energy compared to the potential and centrifugal barriers, which means that I assume that the energy that is here, this term, is much smaller than this part and than this part. So this is just the centrifugal barrier. This is the potential barrier, depends on the coupling. And I assume that this is much smaller than this. Okay? And those two renormalization group equations simplify to now this equation, which is just beta psi is equal to 0. The coupling is scale invariant. This we knew it. And the second equation can be written now just under this very simple form. 2 minus d, d is the dimension of the space. This g minus g squared minus zeta, and this zeta again is the parameter that we described since the beginning, which is defined by this. I can factorize it, and factorizing it, I define zeta plus and minus, which are just here. Okay? So it's simple algebra. And now I can look at the evolution of the coupling G of L. So I remind you that this guy is just stands for this logarithmic derivative, which is equal to this, which means by solving this equation, in principle, I know how G of L behaves when I change the length and I go down to 0. Okay? So this accounts for the change of the boundary condition. Now, if zeta is smaller than this critical value, which is here, then we see that we have two real fixed points, which means that this function vanishes at two values, this value and this value, which are real. Okay? And then we get a complete and well-behaved solution of the Schrödinger equation. And then everybody looks at me and said, but there were a problem at the beginning. What was the problem now? You know, you just, we are in all those solutions, but we don't remember what was the problem. So what was the problem? The problem was that, so here you see there is this value. The problem was, when we looked at this spectral problem, that we assumed that this was larger than this, which means that this lambda squared was a positive. So here it was, in this condition. Okay? Whereas in what I said now, zeta is smaller than this critical value. So if it is smaller, then I have no problem. But if it is larger, then I have a problem. Then you may say, okay, what is the physics? Where is the physics here? I got lost. And tell you the truth, I also got lost. So when preparing the talk. So where was the problem? The problem came from the initial potential. So let me remind you. The potential initially, the strength of the potential is psi, this psi here. When this psi increases, then this zeta, which is this combination, also increases, right? And eventually, this value becomes larger than this fixed parameter, okay? And this is where is this problem, which means that when the potential becomes very strongly attractive, then we start to have a problem. When it is mildly attractive, then there is no problem, okay? So this is when this is realized, this is when the Hamiltonian is not self-adjoint anymore, and this is when this continuous scale invariance breaks into a discrete scale invariance, and we get this Efimov spectrum. Okay? So now, what is the meaning of the renormalization group equations if we remember that here is the physics of the problem? Okay? So, again, this is not this limit that we have to consider, the limit where this zeta is small, but instead we need to consider the limit where zeta is larger than this critical value. This is where we have this problem of self-adjointness. So in that case, if zeta, to summarize what I said, if zeta is smaller than this critical value, then we have two real fixed points, and then we have a complete and well-behaved solution of the Schrödinger equation for the case of a weakly attractive potential. everybody is happy. But when, in fact, zeta is getting larger, in fact, those 2 points merge into one single point. So this curve, instead of having 2 fixed points here, has only 1 point at this critical value. And when now zeta is larger than this value, in fact, we are on this curve. So there are no fixed points anymore. You see that those fixed points disappear. Okay, we have no fixed point. And those 2 values become complex. So now is the instinct. When something becomes complex, there are fractals. Okay, this is here that the fractals comes in. So the solution, if we are in this limit, the solution for this G of L, for the solution of this equation, is now a limit cycle. So this is the solution, just to show you that we know how to calculate things. And in fact, if you look at this, the behavior of this G of L as a function of L, you see that it's a periodic function. And we get a new value each time that we change L, the cutoff, by this universal value. Okay? So this is again where this continuous scale invariance breaks into discrete scale invariance, what I showed at the beginning. Now, the way to interpret it using the renormalization group picture is to say that this breaking of continuous scale invariance, previously understood as a requirement of self-adjointness, is now interpreted as a transition of the RG flow from a unstable to stable fixed point into, in fact, one fixed point here, and eventually limit cycle solutions when zeta is very large. Okay? And when we are here, then directly solving this, we get immediately the Efimov spectrum that we got previously. So it's just a consequence of this renormalization group equation to get this spectrum. Okay, so again, this spectrum results from the fact that instead of having fixed points, now we get limit cycle solutions. Okay? Okay, so now this is the end of part 3. So again, you are allowed to wake up, to refresh yourself. We are going to move to another subject. Now, what I want to show is something that apparently is related. So to discuss the case of the Dirac equation and Coulomb potential. So you see already when I'm coming up to. So the idea, we saw that this whole issue of Efimov physics is based on the fact that this Hamiltonian has continuous scale invariance, okay, to summarize. And now a natural question is, what about the Dirac equation with a Coulomb potential? Why is it a natural question? It's a natural question because we know that Dirac equation is first order in the momentum instead of second order here for the Schrödinger equation. And if now we put a Coulomb potential, which is 1 over r, where the strength of the Coulomb potential is just the charge times the fine structure constant, then apparently we have the same problem because there is no scale in this problem because this is 1 over r and this is 1 over r. So here, this psi is dimensionless again. And these two problems share the same continuous scale invariance property. Okay? So now the question is, do we get something weird, as I just said before, because 1 over r squared we don't know. But here, we learn at school, or we teach students, that we know everything about the Dirac hydrogen atom. There is nothing left out. We know everything. So where is the bug? Okay? So do we know everything about the Dirac hydrogen atom? Well, the point is that this is a very old problem. In fact, usually we don't teach it very much. It's a problem that goes back to Pomeranchuk in 1945, the problem of a relativistic electron in what is called a supercritical Coulomb potential. So let me remind you a few basic things about QED, quantum electrodynamics. The success of quantum electrodynamics, in fact, lies in the domain of small fields and in perturbation theory. And why it is successful? Because we do perturbation theory in a small dimensionless parameter that is called the fine structure constant. And this fine structure constant is the ratio of fundamental constants, the charge, Planck constant, and velocity of light. And this is a small parameter, just a number. And all the calculations involving bound states of a nucleus of charge Z times E, in fact, instead of being in perturbation using this parameter, they involve the dimensionless combination Z alpha. Not only alpha, but Z alpha. And the point is that alpha is very small, but if now Z is so large that Z alpha is larger than 1, then perturbation theory fails. Okay? And in that case, this is this Pomeranchuk prediction, we expect instability of the vacuum, of the ground state, against creation of electron-positron pairs. Okay? So this is an old problem. The problem is that in order to observe this instability, we need to fulfill this condition that Z alpha is larger than 1, which means that Z, the charge of the nucleus, is larger than 1 over alpha, which is of the order of 137. But the problem is that we don't have such stable nuclei at disposal, which means that it's difficult to see this instability. Now, the idea is to consider instead analogous condensed matter systems with an effective but much larger fine structure constant. And the idea came that for graphene, which is a very popular nowadays condensed matter system, then we have effective massless Dirac excitations, but now with a Fermi velocity, which is much smaller than the velocity of light, and now there is an effective fine structure constant that instead of being E squared divided by H bar C is A squared divided by H bar VF, and now this fine structure constant is much larger than the previous one, and this is equal to 2.5, which means that the critical charge in order to observe this instability predicted by Pomeranchuk is now equals to 0.4. In fact, equals to 1 because we have to include screening effects in these condensed matter systems. And this is much easier to achieve than this value, which is here. Okay? So this idea with graphene, in fact, was an excellent idea. It's not mine, in fact. And the idea is the following, is that if you look now at charge impurities, Coulomb potential in graphene, okay, then we get quasi-bound states, scattering of those quasi-bound states. This implies that we have a singular behavior of the total phase shift, the total scattering phase shift. Now, people that came in the last lecture, they know that if you know the total phase shift, in fact, you know everything about the change of spectral and transport properties using this Krein-Schwinger formula. And if you can relate transport properties and spectral properties to this, which is what those gentlemen, Shitov, Katznelson, and Levitov did in 2007, then in fact you can, by a local measurement of the density of states using STM spectroscopy, measure this instability, which is something that has been done recently by this group. Okay, so this exists, this Pomeranchuk effect. So now, how to understand this instability? So I just said that there is an instability because you believe me, because you like me very much, I hope. But I would like to understand more with a simple argument why perturbation theory fails for these values larger than 1 and when we have an instability of the ground state. How to understand it? So I will use a very heuristic argument of this so-called Dirac-Kepler problem. And the heuristic argument goes that way. You take the classical expression for the energy of an electron of mass m and momentum p in the field of the charge Ze. So this is the classical energy of a relativistic electron. And you estimate the ground state energy by just using the fact, as usual, that the electron position cannot be determined to better than h bar over p. And therefore, the energy is always larger than this value. Okay? And by minimizing with respect to p, you get that the ground state energy is equal to this value. Now, this expression reproduces well-known features of the hydrogen ground state in the non-relativistic limit, when this guy is much smaller than 1, and also in the relativistic limit. In fact, it works. I mean, this is exact. So this is just, should not get too much credit to this. And what you see is that for Z alpha larger than 1, what I said before, the ground state energy becomes imaginary, and therefore there is this is the sign of this instability that I just discussed before. Okay, so now an important remark for graphene is the following, is that you may be surprised that this instability is independent of the mass of the electron. In fact, you can convince yourself that just by dimensional analysis that it should be so. And the fact that it is independent of the mass of the electron means that this Dirac-Kepler instability remains true in the so-called Weil-Kepler problem, which is the same problem when the mass is equal to 0. And this is good news because in graphene, Dirac excitations are massless, so we can use the same idea. And what we, in fact, claim is that this instability in the Dirac-Weil-Kepler problem is an example of spontaneous breaking of continuous symmetry into discrete symmetry. Okay? So, in fact, we did the calculation. So this is the idea. The question is there an Efimov-like structure for the massless Dirac problem? So we solved the Dirac equation in a scalar electromagnetic potential, which is just given by this Coulomb potential. And in fact, instead of using self-adjoint extension, which is a kind of cumbersome description here, the renormalization group picture is very simple here to implement. This is what we did. And what we obtained, so I spare all the calculations, which are exactly at the same level of what we did for the Schrödinger equation. We obtain spontaneous breaking of the original scale symmetry into a discrete one with a corresponding Efimov spectrum, exactly as we did before. Okay? And now, for those of you who are interested, it would be very interesting to observe such an Efimov spectrum for this case with graphene, or with something that is equivalent to graphene using, I don't know, cold atoms, something like this. Just okay. So this is about this Dirac problem, and now I would like to wrap up and to just summarize and to give further directions of all what are the two examples that I said. So what I have shown here, I have given two examples of how a continuous conformal scale invariance is spontaneously broken into a discrete scale invariance. The Schrödinger problem with 1 over r squared, attractive, and this Dirac Coulomb problem. For these examples, this breaking of scale invariance can be understood as the need of new boundary conditions to restore self-adjointness of the Hamiltonian. And now, so there is another way. So for people that are aficionados of mathematical physics, there is a very, very powerful tool in order to discuss all these problems, which rely on what is called the deficiency indices and the theorem of von Neumann. So for people that like this, it's beautiful mathematics to do this, just to discuss the same problem. The other thing that I did is that, in fact, to show that the breaking of the continuous scale invariance can also be interpreted using the renormalization group picture as having stable fixed points which evolve into limit cycles, which are described by complex valued exponents, which are, as I said, again and again, characteristic of fractal structures, underlying fractal structures that we may not know at the moment, but exist. In fact, I may give you the impression that I'm the first to say something about this, but it's not true. Far from it. In fact, one of the founding fathers of renormalization group, Ken Wilson, said already in 1971 in a beautiful but very long paper of renormalization group and strong interactions, in which, in fact, he raised this idea of limit cycle as a possible issue in strong interactions. So I know that Antoine knows this paper. And okay, so as I said before, when I introduced renormalization group description, I said that a large number of problems can be described similarly as, in fact, conformality lost. So here I took the title of a recent paper by Kaplan et al. It's called Conformality Lost, and to see the emergence of limit cycles. So there are a few examples like this. One example, in fact, is a Kosterlitz-Tarless transition. So remind you that Kosterlitz-Tarless transition is the deconfinement of vortices in the XY model at a given critical temperature, above which the theory is conformal. And by mapping this problem, this XY model, and the t equal to 0 sine-Gordon problem in 1 + 1 dimension, given by this Lagrangian, in fact, you can show that there is also a breaking of continuous scale invariance into a discrete one. Another problem, set of problem, is the metal-insulator transition in d dimensions, the transition between electron gas and the Wigner crystal that can be described in the same way, and the localization transition. In fact, this idea was brought in many years ago by Gérard Toulouse here at Orsay at the time. There is another well-known problem. It's this so-called Breitenlohner-Friedman bound for massive, free massive scalar fields, but on anti-de Sitter space in d + 1 dimension, where there is exactly the same breaking of continuous scales invariance into a discrete one. And there is this quantum gravity that I discussed in the second talk. And I remind you what we discussed. If you remember, so this is the slides that I took from my second talk. We said that we looked at this path integral, functional integral for quantum gravity with this classical Einstein-Hilbert action, if you remember, which depends on two constants. One is the Newton constant, this one, and one is the cosmological constant here. We said that it's a very hard problem. We said that there are several approaches on the market, and one of them was this asymptotic safety promoted by Martin Reuter and Frank Sauersig recently. And what I showed is that by doing a renormalization group for those two constants, they obtained this nice renormalization group picture with a fixed point here. And when now you expand close to this fixed point, you see again that you have this complex valued exponent and log periodic behavior. So if you remember, I told you at that time, just by measuring this return probability, we get a spectral dimension of a fractal and all this. Here I can be a little bit more elaborate. I in fact show that we have here all the ingredients of a fractal behavior for spectral quantities at the Planck length from this RG description. Okay, so what I did not yet discuss, so don't worry, I do not intend to add another lecture. So there are in fact a lot of things, which perhaps are, I mean, a little bit more technical than the level of the lectures that I try to bring here. One issue is something that is close to my heart. It's a problem in quantum mesoscopic physics. In fact, shot noise in quantum mesoscopic physics. So for those of you who are specialists in this problem, so I can allow myself for 5 minutes to be extremely technical. So there is what is called the Fano factor for shot noise in quantum mesoscopic physics, and we know everything about this Fano factor in 1D. But beyond this, the sky is the limit. We don't know much. And in fact, it's possible to look at out of equilibrium fractal structure and to calculate this Fano factor and to see if it is universal or not. The answer, it is not universal. And this is related to this electrical exponent that I discussed in the first lecture, as an introduction of how many each physical quantity is related to an exponent. But I brought also this example, again, for those of you perhaps who are interested in beautiful mathematical objects. So all this can be described is what is called Dirichlet forms. And this is an entire field of research in mathematical physics, which is just really beautiful. So this is just, I wanted to describe this. Second point that I did not discuss too much, I discussed quite in details what is called diagonal Green's functions, return probability and all this. But I didn't say a word about off-diagonal propagators. And in fact, we know how to say a lot of things there. And so this is, again, this could have been a lecture by itself. And this is very useful, in fact, in statistical mechanics. And this is a series of works that we have been doing with people at Jussieu, Raphaël Voiturier, and Olivier Benichou. And then the last thing, which was in fact supposed to be my third lecture, but it was not, it's about the problem of long-range correlations in disordered systems. So the idea was to look at phase transitions on fractal structure, whatever they are geometrical or not. And the related issue is this idea of long-range correlation. So each time that we look at disordered system, usually we work very hard in order to have short-range interactions. But now that people have been looking at localization transition, for instance, Anderson localization transition in other systems, such as dipoles in semiconductors for the group of Georg Maret in Germany, or cold atoms, like Robin Kaiser is doing at Nice, in Nice, then we have to take into account those long-range correlations. And in fact, in order to know if the disorder is relevant or not in that kind of systems with long-range correlations, we have, in fact, to generalize something that is called the Harris criterion, and in what is called the, what I call, or I don't know if you call the Harris-Luc criterion for Jean-Marc Luc, Saclay, about the relevance of discrete scaling symmetry in such problems. And in fact, here there are, again, really beautiful set of connection between this kind of problem and the connection to substitution matrices and quasi-periodic order, exactly the same way that I presented it in the last lecture, and the topological connection to this. So this is really something that I like very much. But I think at that point is perhaps a little bit too technical to fit into the format of those lectures. And with this, I thank you very much for your attention for all the lessons.